We're down the home stretch. We've done problems 1 through 5. We're now moving on to number 6, and we're finding a Taylor series that is centered at a equals 2. And I use C sometimes for my Taylor series, but it really doesn't matter where you start, what letter you use. But I always write it out as a C. We're going to take the nth derivative at 2. This is our Taylor series that we're going to be having. And we need to do it for e. So our function is now e to the x over 2. Right? So we're going to be writing this out as a Taylor series centered at 2. And then we're going to find the interval convergence. Okay, this will be fun. Now, the key thing for us first is to think about, you could do this first. The order doesn't really matter. Because you're going to eventually, whether you write this out first or whether you actually find the derivatives first. Doesn't really make a difference. Ultimately, the most important thing for you to do is find the pattern, because most of the they said find the Taylor. So when they ask you to find the Taylor series, in general, that means find the general term. We want to find. Often, the instructions will often say, write out the first 3 terms and find the general term. But in this case, they didn't tell us that, so that just means in general you should have the general term. So in general, find the general term. I know. Okay, so that's the function. This derivative is going to be e to the x over 2 times the derivative of x over 2, which is 1/2. F double prime is going to be 1/4 e to the x over 2. F triple prime is going to be 1/8 times e to the x over 2. Now we want to evaluate these at f of 2. So what does f of 2 equal? Well, f of 2 is just going to, when you plug in 2, you're going to e to the 1, right? E to the 2 over 2, which is just 1. What are you going to get here when you plug in? When you plug in 2 here, you're going to get 1/2 times e to the 1. Well, here it's going to be 1/4. Triple prime of 2 is going to be e to the over 8. So now we're going to come in here, and we're going to just substitute them in. We're going to have e over 1 times x minus 2 to the 0. Oh, what's x minus 2 to the 0? That's just 1. All right, let's get that out of there. Next, f prime of 2 is going to be e over 2 over 1. So e over 2 times 1. Okay, now the next one's going to be e over 4 times 2 factorial times x minus 2 squared. E over 8 times 3 factorial. Now, I think I'm seeing the pattern, right? I think I see the pattern is going to be, I'm going to have an e. I'm going to have 2 to the power of n times n factorial times x minus 2 to the n. And that fits the pattern, right? E to the first, 2 to the first times 1 factorial. Yeah, it fits the pattern for all of these. So a way of writing this, if we wanted to, right? If we wanted to write this out in a summation notation, it would be like this. To check, I really should plug in 0 to make sure it works. That's going to be 0. Yeah, it does work for 0 too. Good. Okay. So I always like testing the first term because the first term doesn't always work. So I kind of feel like we're done, except for we're not, because they also asked us to make sure that we find the interval convergence. When does this true? Well, I kind of know the answer off the top of my head because I've done these problems before, but you don't, so I have to show you. So we're going to take this expression right here, folks, and we are going to do the ratio test. We're going to have e over 2 to the n plus 1 times n plus 1 factorial times x minus 2 to the n plus 1 multiplied by the reciprocal, which is going to be e to the, sorry, the 2 to the n goes here. And down here, we get that x minus 2. And then I'm going to cancel that a lot. So the e's cancel. The n plus 1 and the n factorial cancel just to n plus 1. So the e's cancel. The 2e, the n plus 1, and the 2 to the n leaves us just a half. The x minus 2 and the x minus 2 leaves us an x minus 2. And then this n plus 1, that, ooh. What does that equal, folks? Well, as n gets really, really large, no matter what this number is, this is going to go to 0. And this means this, just like problem, what was it? Problem 3e, yeah, just, sorry, 5e, just like 5e, which we did in the last video, this converges for all x. Because no matter what, we have a 0 and it's less than 1. As long as it's not infinity, right? As long as we can get to infinity. The first 5 non-zero terms of cos of x. Now, the only reason why this is slightly challenging is because they made it at pi over 4, right? Because we know the Maclaurin series for cosine. I mean, we should have that one memorized. 1 minus x squared over 2 factorial plus x to the 4th over. That's one you should have memorized, the even one, and sine being the odd one. But this one, they didn't give it that way, so we have to write it out because it's evaluated at pi over 4. So this one's going to be a little bit different than the Maclaurin series, which is centered at 0. Oops, what am I writing that there for? You know, I'm going to write these first. I told you the order doesn't matter when I did 6, so I'm going to write these first. We have cos of x. We have negative sine of x. Yes, for the first 5 terms. That means I need to do one more. I mean, some of you see the pattern. You don't need to do it all out, but we have to now evaluate this derivative or the function at pi over 4. And the good news, pi over 4 is easy, right? We know it's always root 2 over 2. So I'm going to use a different color. F of pi over 4 is root 2 over 2. F prime of pi over 4 is negative sine of pi over 4, which is negative root 2 over 2. This now is going to be negative root 2 over 2. We're going to be plugging in here for f double prime. F triple prime of pi over 4 is going to be back to positive. So it kind of alternates every other one, right? So thank goodness they're only asking for the first 5 terms, because this would not be fun to worry about the signs, I'll tell you that. How do you write that out where it's like positive, negative, negative, positive, positive, negative, negative, positive, positive? That would be hard to write out. So luckily they didn't ask us for the general term. Thank you. Appreciate not having to write that out. So the Taylor series is going to be like this. The Taylor series centered at pi over 4 is going to be f pi over 4 over 0 factorial times x minus pi over 4 to the 0. And this is not necessary, folks. Why am I taking my time to do this? It's because this is a solution guide. There are many of you that would not take this time to do this, and nor would I expect you to write this step out. This is just a workout for my hand muscles more than anything else. And they ask for the first 5. 1, 2, 3, 4, 5. Okay, take a deep breath. Now we're going to plug in root 2 over 2. That's 1. That's 1. Root 2 over 2. Oops, no, I lied. That's now negative root 2 over 2. Let's change the sign. Over 1. You don't have to actually do any kind of balancing. You don't have to try and bring like terms together. Just leave it like that. Minus again. But root 2 over 2 times 2 factorial. 2 times 2 factorial is 4. This one's now back to positive, right? We're back over here. Now we're positive. Root 2 over 2. With the 2 being multiplied by 6. And we're staying positive. 24 times 2, 48. So I think those are our first 5 terms, folks. You will sometimes see that some people will write this differently, and you could write it so many different ways. You could, if you want to, not multiply the 2. You could write it 2 times 1 times 2 times 2 factorial, 2 times 3 factorial, 2 times 4 factorial. That's totally fine. You could factor out the root 2. You could factor out the root 2 over 2. You can write it many different ways. So I don't want you to think there's one way to write this. This is the way that I would write it because it's intuitive to me. That doesn't mean it's the way that you need to write it. As long as that if you multiplied it or factored it, you get the same thing, you're in fine shape. Okay, this one is good. This one is really good. This is one of the things why I told you, you really just want to get these down. You do not want to spend time, if you're ever being asked to do this, you do not want to spend time deriving this. We've derived it already. I do not want to derive this every time. We derived this as a class way back when we did Taylor series. I'm going to try and jump back real quick to see if I can find it. Yeah, here's where we derived it, right? Way back when we did Taylor series. If you go back up, you're looking for it. It's right above assignment 4, 1, and 2. It's the Taylor series page. It's a couple pages up. But we've done that before. So the good news is I'm not going to do that again. Now I have to come in here and I have to take this, I have to multiply by x squared. Right? If I'm going to multiply this, if I'm coming in and multiplying this by x squared, I'm just going to multiply this by x squared. Of course, this keeps going, right? But they asked us for the first 4 terms. So this is the fastest problem probably in the whole assignment. Number 8 coming in with the fastest problem. Just because they did not ask us for this, but because that problem is so fast, I feel like, wow, I have a few extra moments. If they asked us for the general term, this is not required. I need everyone to know you did not need to do this. But if they did ask you for the general term, what I would have probably done is I would have said, well, the general term, treat this 0. This is 1, 2, 3. The way I would have written out the general term is I would have had 2n plus 1 factorial in the denominator. Then I would have had -1 to the, I guess the 0th term should be positive. And then what I would have here would be x to the 2n plus 3. Just to check, like 0, 1, 2. This is if n equals 2, does it work? We'll plug in 2. You get 5 factorial, positive 1. X to the 4 plus 3 is 7. Good, so it does work. So if you did need to, that's how you would write that out. You didn't, though. I just like adding extra work for myself. You do have to here, though. All right, so this one here, we want to know e to the x. Go to that same page. This is one of the ones that you want to have down. It's kind of funny. One time I told students, you need to have this down and memorized. And I wrote this on the board, and I started doing the whole problem, and I got to the very end, and no one stopped me. And at the very end, someone said, Mr. Popek, I think you have your signs wrong. And I did. I was alternating the signs the whole time, and I made a huge blunder. So I hope that's correct. And remember, this is x to the n over n factorial. So to do this problem, step 1, we now come in, we say we're now using e to the negative x squared. Okay, so now we're replacing all the x's with x squareds. So this is now negative x squared instead, plus negative x squared squared, plus negative x squared cubed. I always deal with the function first. Oh, there's a 2 there. I always deal with the function first, then before I do the multiplication. So this is 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th. Some people like writing it this way. I think writing it that way is actually pretty beneficial because once in a while you're asked to take the derivative of this. If you're asked to take the derivative of this, it's nice to have a clean x, right? So then you just take the derivative of this by subtracting 1 and doing your power rule that you do when you take the derivative. And now someone comes in and says, take this now divided by x squared. So you're like, okay, divide that whole thing by x squared. No problemo. I'm probably doing more than I need to do. And now this should be negative 1 to the n, x to the 2n minus 2. There we are. So that's how you could write this series. You could write this other ways too. If you wanted to, you could come in here and write it as a summation notation, right? And if you wrote it as a summation notation, we have negative 1 to the n, x to the 2n minus 2. We're just using the general term, right? We just make sure we start at the right place. Plug in, we're going to infinity. 0, right? And plug in 0. Comes negative 2, 1, yep. And that's how we could write that one out too. So, I mean, frankly, I would probably leave this if I was asked that, but another person could write that, and that's what the answer key looks like it has too. So both answers are totally fine. Wow, we're done. That was fun. I hope you enjoyed as much as I did. If you have any questions, you know what to do. Just come and ask. Take care.